St. Petersburg was built by Peter the Great as a statement. In 1703, he chose this site specifically, a marshy delta at the mouth of the Neva River on the eastern edge of the Gulf of Finland, because it was the worst possible place to build a city. The ground is soft clay and peat. The water table is practically at the surface. Building anything here at all requires driving piles down through meters of unstable soil just to find something solid enough to stand on. Peter knew all of this and built anyway. That's the city. So when Gazprom decided to build the tallest skyscraper in Europe in St. Petersburg, they weren't just dealing with the usual engineering problems of a 462-meter tower. They were dealing with all of those problems on some of the worst foundation conditions on the continent. The Lakhta Center sits about 9 kilometers northwest of St. Petersburg's historic center, right on the shore of the Gulf of Finland. The site was formerly a sand storage yard. That detail is important. Sand over soft clay over more soft clay with groundwater sitting half a meter below the surface. Before any construction could start, engineers had to understand exactly what they were working with, so they conducted extensive geotechnical surveys, boring test holes, extracting soil samples, measuring the water content, compressibility, and shear strength of the layers below. What they found, roughly, was this: a thin surface layer of sand, underneath which are thick sequences of soft quaternary clays, sediments laid down by glaciers and sea transgressions over the last 10,000 years. These clays are compressible, meaning they deform under load over time. They're also sensitive, meaning if disturbed, they lose a significant portion of their strength. Competent rock, the kind of material you'd want a 670,000-ton building to ultimately rest on, is not easily accessible here. You have to go deep to find it. This is the fundamental problem the foundation engineers had to solve. How do you transfer the weight of Europe's tallest skyscraper safely down through tens of meters of soft, compressible ground? The answer was piles. Very large, very long piles. A bored pile is exactly what it sounds like. You drill a hole into the ground, lower a reinforcement cage into it, and fill it with concrete. The pile then transfers load down through the weak upper soil layers, partly through friction along its sides, and partly by bearing on whatever stronger material it reaches at the bottom. For Lakhta, 264 bored piles were installed under the tower alone. And these are not ordinary piles. Each one is 2 meters in diameter. To put that in context, most bored piles in standard construction are 600 millimeters to 1,200 millimeters across. The 2-meter diameter here set a world record for this type of pile. Custom drilling equipment had to be manufactured specifically for this project because nothing commercially available could drill a 2-meter borehole to this depth. And the depth is the other number. The piles reach between 72 and 82 meters below ground level. That's roughly the height of a 20-story building, pointing straight down. At that depth, the piles reach into denser, older glacial deposits that can bear the load. The weight of the tower travels down through 264 columns of reinforced concrete, each 2 meters wide, each punching 80 meters into the earth. But the piles alone aren't the whole foundation. Sitting on top of them is what the engineers called a box foundation. The tower has 3 underground floors. These aren't just a basement, they're structural. The underground level is shaped in plan like an equilateral pentagon, with each side 57.5 meters long. The walls, floor slabs, and ceiling of these 3 underground floors all work together as a single rigid box. The purpose of this box is to distribute the load from the tower core, which is concentrated at the center, outward to all 264 piles. Without it, the pile directly under the core would be wildly overloaded, while the ones near the edges barely do any work. The box spreads the force. Before any of this box could be built, the excavation pit had to be kept dry. The groundwater table, remember, is half a meter below the surface. Digging a 20-meter deep foundation pit on the shore of the Gulf of Finland means you're essentially creating a hole that wants to flood. The solution was a diaphragm wall, a continuous reinforced concrete wall constructed along the full perimeter of the site, 30 meters deep and 1.2 meters thick, installed before any excavation started. It's constructed panel by panel. You excavate a narrow trench, fill it temporarily with a heavy drilling fluid called bentonite slurry that holds the trench walls open, lower in a reinforcement cage, and then pour concrete from the bottom up, displacing the bentonite. Repeat for every panel around the perimeter until you have a closed ring. This wall then acts as a watertight barrier around the excavation. The groundwater can't get in. To handle the massive lateral pressure from the soil outside pushing against it, The diaphragm wall was reinforced with four horizontal concrete rings, discs essentially, at different depths, which braced the wall against the ground, trying to push inward. Once all 264 piles were drilled and the pit excavated, the bottom slab of the box foundation had to be poured. And this is where the project entered the record books. The base slab required 19,624 cubic meters of concrete, poured in a single, continuous, uninterrupted operation lasting 49 hours. This matters because concrete is a chemical process, not just a physical one. When cement hydrates, reacts with water to harden, it generates heat. In a normal pour, you let each layer cool somewhat before adding the next. But if you have a cold joint, a layer that has fully hardened before the next one is placed on top, you've introduced a structural weak point. A slab of this size, with rebar running through it, can't have cold joints, so the entire 19,624 cubic meters had to go in as one continuous operation, keeping the pour alive at all times across the entire base. Concrete was sourced from 13 different plants across St. Petersburg. Trucks arrived on a strict rotating schedule, on average one every few minutes, to keep the pump supplied without interruption for the full 49 hours. The reinforcement alone in that slab weighed 9,200 tons. That's roughly the same amount of steel used to build the Eiffel Tower. The pour set a Guinness World Record, beating the previous record held by the Venetian Resort in Las Vegas by around 3,000 cubic meters. Now for the structure above ground and the reason the tower looks the way it does. The Lakhta Center rotates 90 degrees from its base to its tip. 5 lobes, described by the architects as wings or petals, extend from a central reinforced concrete core. As the building rises, these 5 lobes gradually rotate around the core at a rate of 0.82 degrees per floor. Over 87 floors, that cumulative rotation reaches 90 degrees. Every floor plan is therefore slightly different from the one below it. There are no 2 consecutive floors that are exactly the same shape. The facade cladding, 16,505 individual cold curved glass panels, each a parallelogram, each weighing around 740 kilograms, has no parallel lines anywhere on the building because the geometry is constantly changing. This is visually striking, but the twist isn't purely aesthetic. There's a structural reason for it. When wind hits a tall building, it doesn't just push. On the downwind side, the flow separates and forms alternating vortices, spinning columns of air that peel off one side, then the other, then back again. These are called von Karman vortices, and the frequency at which they form is directly related to the building's width and the wind speed. If the frequency of vortex shedding matches the building's natural frequency of oscillation, the rate at which the structure naturally wants to sway, you get resonance. The building starts absorbing energy from the vortices and the swaying grows. For tall buildings in particular, this is a serious concern. The twist disrupts this. Because each floor is rotated relative to the one below it, there's no consistent face for the wind to push against. The vortex shedding pattern can't lock onto a single frequency because the geometry it's interacting with keeps changing as you go up the building. Wind tunnel testing of the design showed that the twist reduces wind-induced lateral forces by around 35% compared to an equivalent building with a straight prismatic form. The lateral stability system has 3 main components. First, the central concrete core, a reinforced concrete tube running the full height of the building, housing the lift shafts and stairwells. This is the primary element resisting wind load, acting structurally like a cantilever beam fixed at the base and loaded sideways at every level. Second, the perimeter columns, composite columns made of structural steel sections encased in high-strength concrete running up the outside of the building. The steel core gives them high tensile strength. The concrete jacket adds stiffness and fire resistance. Third, every 14 floors, there are dedicated outrigger floors. An outrigger is a structural wall or truss that extends from the concrete core out to the perimeter columns, connecting them. When wind pushes the building sideways, the core tries to deflect. The outriggers transmit that deflection into tension and compression in the perimeter columns. The whole perimeter of the building is recruited to resist the overturning moment, not just the core. This is a standard technique in super tall construction, and it's one of the reasons buildings of this height are structurally viable at all. The Lakhta Center was completed in 2018. It topped out as Europe's tallest building in October 2017. It won the CTBUH Skyscraper of the Year award in 2020, and the following year took the Structural Engineering and Geotechnical Engineering awards, which feels appropriate given everything we've just covered. The numbers that stay with me are the foundation ones. 264 piles, each 2 meters wide, each 80 meters deep, drilled through material that Peter the Great's engineers would have considered unbuildable. Then 49 hours of continuous concrete, an entire city's worth of mixer trucks running in relay through the night to keep one pour alive across the full base of a 462-meter building.